Alright, so today we are looking at the standard model, and we're going to see how it emerges from our quantum gravity model, where we encoded everything into pure zeros. Alright, so first let's see how we can follow a timeline down. I'll make it really straight. So this is essentially a timeline, and if the timeline had holes in it, here, 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 then what that would happen is allow a imaginary field to pop up here, tangent to this, and of course several other timelines as well. So you could put another one right next to it and sort of make a whole volume of these things, really. One second, let me try to get the transparent selection going so I can stack this a little better, like this. So let's see if I can get like a volume of this type of thing happening. Because remember, we live in like a 3D volume, so how are we getting a volume? Well, here's how we get that volume. If we do something like this, and then you can see how we kind of have a volume forming here. I guess I'll connect the zeros like this. So we can call, you know, this direction. You can see there's definitely abilities to create volumes and stuff. And so this gives us, dx's, dy's, dz's. You could imagine something like this. But it also gives us this area up here with these things that are essentially the quantum field. And not only does it exist there, but as you can see, I was kind of about to draw another one right here. It kind of exists here too. There's another quantum field. But this is further in time. This is the next quantum field. Um, and the goal, of course, is to slide this information down this field. Um, especially if we gave it some kind of curvatures or whatever, if you want. So let's get this looking more like that. And again, put them on the bottom like this. That's not gonna work, is it? Because I'd like to be able to focus all this energy like a magnifying glass in the sun. As the energy intensifies, I want to spawn something in the middle. Um, but forget about these two things. Let's just focus on this primary one right here. I want to be able to essentially pull out numbers from this. So we're starting at 0, real 0. And, well, what did you expect to pull out? Didn't we already draw this somewhere? We said something about ones and zeros, and I already sort of drew the wormhole and stuff and explained how all this thing happens. But I'm trying to pull out numbers from this now. The number should be appearing. Let's see. The number should, essentially be appearing right in the middle, right? If we would really wanted to. should be appearing kind of right in the middle. We could spawn something. I guess we'll make it green, and it should be there. And we should make this thing real nice and symmetric so that we can have this beautiful wormhole forming that's like perfectly hourglass shape and symmetric. That would kind of be the ideal shape. And if we did something like that, we could perfectly Fourier transform from 0 to 1 and then back to 0 again. And it would be essentially perfectly sort of right in this middle here, appearing. Why? Because, essentially the zeros are on the axes here, these points, and the ones is the axis. And just take a moment, sort of take a little drink of water. All right. So, Fourier transforms of 0 to 1 is a little intense because now we're trying to say that, like, we had to Fourier transform. Uh, yeah, it's just a little bit weird. We pulled out like we pulled out a 1 from 0. It's just kind of weird. But that's how we have to do things, I guess. And here's the reasons why. And it's kind of weird. Remember our theories that 0 was supposed to be the Higgs. So the O field, well, the real O field generates the Higgs. And this is correct. If we, um, this is the standard model. We have the 0 field, which is the Higgs. Just have a bunch of O's out there with spin 0. This is their spin. Um, if my theory over here about how all this stuff forms is wrong, okay, that's fine. Here's some stuff that's actually been proven here, that Higgs is definitely spin 0, and it exists in this O field. So now we're definitely back to like normal physics here, so that's cool. And the truth is that when the 0 wants to create particles, it will manifest the 0, or sorry, manifest a 1 out of it. So the Higgs starts on 0, and then it starts to create other particles. So other particles can spin out of it. So let's look at the other particle spins that exist, uh, especially spin 1. Particles that come from spin 1. And here's your green spin 1 that you just kind of pulled right out of there. It's a little scary. Remember that thing right there sends out a shock wave, gravitational waves. Very small, of course. And the curvature here, this curvature is super, super small. In fact, negligible. Negligible curvature. And the little gravitational waves that pop out are negligible. So these effects are so, so, so small at the quantum scale. So just kind of essentially ignore all that's happening there just to be able to pull this information out. Okay? And negligible curvature and the gravity wave is microscopic, essentially. It's a microgravity wave. I guess that's a microgravity wave. And all the quantum information just kind of right in the middle there. You can imagine that. Whether this is accurate or not, I don't know. But at least what happens is particles appear with spin 1. So now we can talk about real physics, right? Let's look at the photon. And here's the key. photon has spin 1, which means you have -1 on this side. That's what it could appear as. Or it could appear as 0. Or it could appear as +1. If you add all this up, you get 0. Particle likes to be at 0. Okay, boom. Photons pop out, the gluons pop out. That would be W plus and minus, and Z boson. These things just pop out from the ones, or from the zeros and the ones. And it could be that this is how that is essentially able to manifest itself. From this imaginary plane that exists over here, tangent to each zero that exists. This is the real zeros for now. This is the real zeros. At each real timeline, we have this real zeros, which is why we have a real field, and that's our Higgs that we can interact, which is nice because it's cool. We got the Higgs; those are real. But then we forgot that there's an imaginary plane in between here, and the gravitons, which are dark matter. It's that stuff that interacts with just curvature. You can call this whatever you want. But there are some imaginary zeros out there, which they gotta be doing something. So I guess we'll just put this here. That kind of needs to be there. I'll just move this here. Alright, whatever. And so now we have, remember that the real field, there was only one way to do this. So if we go back over here, since this real imaginary combo has an imaginary part to it, we're going to ignore it. And we're going to stick to pure real. So we get one form in the real. We ignore the other stuff. These guys, since they're imaginary, and it's got imaginary over here, he's not gonna ignore the real part. He's gonna like take the real part and manipulate that and use the imaginary part. So this thing, he has two forms. And so that's why we get the Higgs only gets one axis, 1, 0, whereas the graviton, it's a two form. Hmm. So it gets a spin too. Theoretically, this is kind of what they've agreed that the graviton wants to have a spin too, because it interacts with two dimensions. Well, in a sense, because it needs a 2 by 2, a 2 morphed with a 2, like this, which provides a 4 form. Anyway, uh, don't worry too much about that. So what we get is spin 2. We'll discuss all that stuff later, how the forms combine together. But for now, we will discuss the spins, because this is a little bit more. real. Let's just kind of consider this dark matter stuff for a moment. Maybe the gravitons exist, maybe they don't, but this is how spin works. You get to add another, you get to add another number down there at the bottom. I'm trying to figure out this thing. Yeah, whatever. And then we could put the next stuff, -2 and +2. What's up in here? Oh my god. 1 second. Oh, okay, perfect. Now we have this, and I will put this on the other side. The plus sign, and we get to extend our spins a little bit. Unfortunately, yeah, something like this. So, there's just a mathematical framework that allows for this to happen. We have a lot of trouble interacting with the imaginary dimension. It, it's not real. So, like, it's you have to imagine this. The numbers, it can work. If you just manipulate the numbers to your favor, just the way you want it to, it'll just give you this stuff. That's the crazy thing about this. The real stuff is what we can test because it's in reality. The imaginary stuff, like, how are we going to interact with all those imaginary numbers? Well, one way was through curvature. Remember, curvature, that was one way that dark matter interacts with um our world is through curvature. That's the thing that links these two worlds. So, like, you know, we're on to something. We've found it. We've figured it out. We've plotted it in the world. It looks like, chunks of mass, and then there's spiraling halos around it at different, equipotential zones and stuff. They're curved around and things, and there's more and more of them and stuff. But and then inside of them, there's even little ones. Okay, and that's fine because all these things are just basically zeros amassing. These are imaginary zeros, right? All this stuff is just the imaginary zeros, and they're sort of forming together and clustering together. And then they've got these equipotentials because you can see all the imaginary zeros with these different equipotentials just popping up everywhere and spiral and creating basically giant walls. Uh, so this is sort of one way that we can imagine that these are sort of imaginary zeros here. The real zeros we've been able to test and find, the Higgs, this is purely real right here. The spin zero Higgs bosons. Amazing, right? Amazing. We found the real zeros. And the imaginary zeros, they're a little bit more tricky to deal with. So, but we've definitely noticed them, but we haven't been able to put our fingers on them. Okay, so then they give us access to these extra -2 and +2 on the right over here. Okay, these are dark matter halos over here, by the way. Uh, clusters which form these little halos, all sorts of cool things that are sort of like kind of described by equipotentials, um, where like the zeros would sort of spiral around that point, you know what I'm saying? This is more not supposed to be a square. It's kind of more supposed to be a circle because things are spinning due to the e to the I theta nature. These things kind of spin around at angles, and so you can get circles out of it. That's the key. Everything's about circles. You form it into these a square-like form, but these are all circles. All right. So anyway, the eye is what allows us to do this crazy stuff. Um, so, so that these are equal potentials. These are equal potentials. That was the key. Put that somewhere. There's equipotential halos. Something like this. These are just some ideas. Now let's return to these other spins that we can talk about this. Because a spin of a half, or sorry, a spin of one is nice. Because that can equal zero. We could also make this a spin of a half, and we can get a different set of particles. So let's just give it a spin of a half. That's sort of what manifests in between there instead of the one. And if we did that, then we can manifest halves. And well, again, if you add all these numbers up, you get zero. So that's kind of cool. That's what allows you to pop up with all these zeros and ones. You just come back to zero afterwards. So you get zero here, you go to one, you go back to zero. As long as you kind of allow for the negative ones to pop out, and then you can go back to zero, cancel out the energy. This happens with annihilation and creation. These things appear with their particles and antiparticle pairs, balancing the energy, and they're essentially manifested through tunneling, because this is essentially a tunneling effect. Tunneling through curvature, basically, is what they're doing. They are tunneling through curvature, causes these things to just appear and manifest as ones and zeros, or halves and negative halves. And if we did the halves, then we get other particles. We get all the ones that we're familiar with. So we get uh, spin up. You get that spin up one thing happening, spin down thing happening, the electron pairs. So we get the fermions here. About photons, gluons, bosons over here. And then we get the fermions over here. So we get electrons. Then we can get protons. And we get neutrons. Neutrons. Neutrinos. Quarks. So all of these particles pop out of the halves. Pop out of the zeros, which pops up. The halves pop out of the zero, which is just the spins. I don't know what to say. It is what it is. I guess tunneling through curvature causes the quantum fields to have curvature, and the fields have to tunnel through time, And as they do that, they go from 0 to 1. And where, what the heck are these zeros? Remember, this is the zeta function. So essentially, uh, the Riemann zeta function, the zeta zeros, basically wave functions. There's like a singular beast wave function, and he's just on this little worldly, like, he's completely spread out over everything, and he encompasses the idea that, um, he's the entire thing here. We can give him a little purple crown, so he's the big guy. He encompasses everything, and and this guy, he's just like, yeah, what's up? And he says, well, hold on a second, I can't be everywhere at once. That's not really possible, is it? Kind of, kind of not, because he's got all these points, but he can't get zero here, zero here, zero here. Let's not forget they're imaginary zeros, so there's zeros in this little field too. But they're different kinds of zeros. We have trouble interacting with them, so they're these ones. Right, so we have all these different zeros in the zero field that exist in this wave function that exists everywhere all at once that encompasses everything, and it's the Riemann zeta zero wave function that encompasses, in fact, all of the Riemann zeta zeros are an element of this wave function that allows us to mathematically represent grand wave function. So I guess we'll call this the grand wave function. This crazy thing right here, if you use a Hamiltonian on it, you can pull it apart and and find smaller ones inside of it. So you can manipulate little chunks of it, you can manipulate bigger parts of it. Because remember superposition. So he's gonna basically take he can he's equal to this thing right here. The grand wave function is equal to several other smaller wave functions. And they also are smaller bits of them, so you can essentially call this a fractal. So there's essentially like zillions of infinite many fractals, and this continues forever. Riemann zeta zeros, all part of the grand wave function. This is the grand zeta function. It's not the wave function, it's the grand zeta function. Grand zeta function. We'll capitalize the F too because this thing is a beast. Awesome. So you can use Hamiltonians on these micro wave functions that sort of spawn out of it and pop out of it. And so you can calculate those quantum numbers. These are just fractals. You can add them all up to create a huge wave function. Let's give them numbers too, so it's a little bit more real. 0R, and these are basically infinitely many of them. We'll call them Rn, comma, and there's there's another one. We'll give it the IM. Something like this. I, and we'll use the M's here. Ah, and now we can just put a column between them if we want to be extremely formal. And then just go ahead and pop them right there. Now we have formalized this a little bit more rigorously. Essentially, there's like a set that pops out, set of zeros. Then whatever. Let's just call it a day here with all this stuff. Let's go ahead and continue with the other things that we have to talk about. This is just a lot of stuff. Down, house, photons, electrons. These wave functions. I do want to describe how the interactions happen. Because these gauge interactions come from these things. Remember how we presented this, how we have to get these groups to work together. So these things here are gauge interaction matrices. Where does this pop out from? We needed a minimum of 11 dimensions to be able to describe everything. Why? Because of this pairing right here. The four forms. Actually, this is really important. So this is why it's critical to sort of count these dimensions out properly and to just say, did I represent with the minimum possible? This is the minimum. To be able to represent all of this mathematically, the minimum necessary is 11 dimensions. Go less, you're describing something incomplete. If you do more, you're just making a linear combination of what you already know. So it doesn't matter. Okay, so if you do less, it's incomplete. If you do more, it's just repetition. Okay? So if we have 11 dimensions, what does that mean? It means that we came up with a four form right here that has time and XYZ. That's four dimensions. Okay, so we pop that with four here. This thing right here is complex. Look how many it has. 1, 2, 3, 4, 5, 6, 7. So there's actually 7 dimensions that pop out of this pairing here, this four form. Yeah, it's just a four form, but it really has 7 dimensions within it. Over here, this is just combinations of these things, so you can properly get the interactions to work. These things allow you to make combinations of these and basically multiply them as matrices together. Move this a little bit on the spot. Over here, something like that. Uh, So essentially, derivative combos. You take just any combination of three. You can set two of them equal to zero if you want, and so you can get just the U1 matrix. The U1 is just a one by one. So what it does is essentially it sets these things equal to zero, and it just looks at the interactions that you can use with just one there. This one is a two by two, so now it's working with two of those, and it pairs with that other stuff, and find some interactions between that. This is a 3 by 3 matrix, and these are the matrices. So this matrix arrangement here is represented by all the possible numbers that can be represented by this particular 1. This literally just equals 1. We can figure this out mathematically. Let me see if I can get the exact equation so I don't say something crazy here. So the real question is, how does e to the I theta represent 1? I think it's better if we just say something like, if you put 0 here for theta, you get 1. So, science vectors. Let's see, if I put something like this, essentially I can get something that's really similar to it. I've just sort of rotated it in a way. I can rotate something like this. So, um, this is how it looks a little bit better if we get the math right. So we say something like, this is the power of the U1 matrix. All the ways that we can make this little rotation, and where e to the I theta, and then get the absolute value of this, that's going to be equal to cosine squared theta plus sine squared theta, and then you take the square root of this. I mean, all this stuff doesn't really matter so much. It's just that, like, this, if you take the absolute value of it, it's equal to 1. So that's what the U1 matrix kind of gives you. Here's the matrix. 1. Or, just like this. Just plug it in there. See if I can represent this U1 matrix slightly more mathematically, because I want a good representation. It says U1 let me get this one. U theta equals e to the I theta. Alright, beautiful. You put whatever theta you want in there, and then you get e out of theta, and then it's just equal to 1. Follows. That's essentially what we're doing to the time, is we are rotating it at each 0 point. Alright. So that's the U1 matrix. And this is the transformations that allow the electromagnetic uh, interactions to occur. Electromagnetic interactions. Um, these eigenstates. Let's look at SU2 for a second. Now, I had written these on a different sheet because it was in modern physics. The SU2 matrices are down over here. They're Pauli matrices, and this is kind of how you're able to manipulate this wave function and left-handed fermions are able to function with it. So this is kind of more about how these things work together here. But I don't really want to go too far into it. Here's a nice picture about how the U1 group works out. That you take your wave function and you multiply it by the U1, and mathematically that's just saying you just multiply the wave function by 1. It's supposed to be a theta there, not a 1, but I guess, I don't know, whatever, it doesn't matter, this is how it works. And then you can see how this thing just kind of rotates around, wherever you want it. And as that happens, you have to shoot out a little pulse, and it took some energy, but it's the same magnitude, so that's kind of what happens there. These things, I believe, they flip the states here of the fermions, and so you get the anti-fermion or the fermion version, and so you could pull those things out. This is how the interaction works here. And then for the strong, it's similar, but this time you're working with RGB, and you're just switching between the three numbers. These are kind of cool representations in terms of like the cubes. Say like this cube has different like ways you can look at it, but it's still the same cube. You're just looking at different sides of it. And it shoots out the different colors, literally. Like that's light. Like okay, now red light. Oh wait, you can shift it to blue light. Oh, you can shift it to green light. So you could shift this light around, but it's still the same cube. If you go to just the pure SU2 uh, by itself, it's only able to flip things from black to white. Okay, so you could flip that back and forth. And so you only get two colors here, and you have to kind of arrange that or whatever. Over here, this one is the electroweak. This is the combination of these two working together, so you can actually still get meaningful results if you combine both of those two things. Then all of a sudden now your cube, instead of being just black and white, it gains colors. So that's pretty nice. And so this is the interactions that you're able to get between these types of particles, like um, electrons and anti-electrons. And then over here, this is the strong. So this is the Gell-Mann matrices, which are 3 by 3s. And the this only affects quarks. So like this is more like a triangular thing where it's like there's only 3 things you can be at, but it's still a percentage chance. It's kind of like a 3 by 3 cube, but it's actually got 3 colors to it or whatever. And yeah, and so now you're kind of just solving a regular old Rubik's cube here, 3-colored one. So you kind of have to deal with these Rubik's cubes in the standard model. 1 by 1s, the 2 by 2s, the 3 by 3s. We're still trying to achieve how we can combine all those together so that you can make them. Well, let's not go too far into it, but essentially this is what we can do with this. Right? Let's head back to what we were trying to define over here. Do we really need to explain everything now, how this all works? Probably not necessary mathematically here because I already had that written down. But just a reminder that this was working with the EM. This is the, what is it again? I think it's just pure weak. Yes, just the weak. And then you can combine these to get electroweak. And then, you can look at just this one by itself, and this is the strong. And I think they're struggling. We're struggling now. Because how can we combine this further? Well, they thought to themselves, okay, maybe we can put this in flat space and we can get both the electroweak and the strong working together. And so they managed to kind of get that to work. So they get the relativistic QM in the Dirac equation. We got the Dirac equation. What I'd like to see though is I'd like to see these Dirac equations. Let's take a look at the covariant derivative. So we have B mu equals partial mu minus I G A mu, where this is the gauge fields. Gauge fields. The G here, I believe all gauge fields work with this form. This here is a coupling constant. And then we have the photon interaction. Some way that we can do that. Well, we're just going to use this equation again. Take this equation and give it some meaning. So this thing now becomes the real I'm not 100% sure about how this works. I should I get this right for the photon interactions. So for the direct photon interacting one, a um, so this A thing, this is the four potential. Four potential gives rise to the electric and magnetic fields. It has components. So let's see what this does. I've always wanted to figure out what this A thing was, because this thing is very interesting. I see it all the time. So it's basically A0. Okay, A. What are these A's? Put an A here. This is A0. And then there's an A. This is an A vector. Mhm. So it looks like we have scalar and vector paired together. So the scalar and the vector paired together. Excellent. That's what's most very interesting. It's a one form with a two form, a scalar and a two form. One form with a two form. That's very interesting. Uh, well, I guess this thing is the one form. I don't really know. Hold on a second. One form seems to be small and it's not really like that, I guess. It's not like that. It's more like that this is a one form here, and that the two form is the electromagnetic potential. This stuff is all very confusing to me as well, so don't worry. One form and so this is actually an O form, and this is the vector potential one form. Okay. When combined into a single object, the four potential, it becomes a one form. We can combine this into one object by doing it like this. Let's say A. Still haven't even labeled A, have we? Just the pure A by itself equals a mu. This one. A mu dx. So you take the derivative in the mu directions. You put it into one, and then now it becomes a one form. I think this is how we had to do it. Net potential is the four potential. Now, why do they call it four potential? Okay, because I guess because it has one scalar and it has a vector that has 3 degrees of freedom. You know, it's a 3D space-time. 3D space, really. Really. It's 3D. Yeah, I think this gives you time and this gives you space. I think that's what we do. That would make more sense. I'm just trying to get this to work out. This is like a little bit crazy. So we go from one scalar is time, and the vector is 3D space. Um, Time is this is the scalar, which is the time component of the four potential. Scalar potential is the spatial component, which is a three-dimensional vector in a 3D space. Yeah. Yes, this is right. It's four potential combines these two, so you get this. This A thing has components. You can call it A, B, C. You know what I mean. Doesn't really matter. This is a 3D space, blah blah blah. And then Shazam, and we have the one form, which is A, just A, which takes this thing, takes derivatives, and combines it into the one form. Okay. Very confusing, but that's how the photon interactions work, I guess. It's the electromagnetic field. This is relativistic quantum mechanics or something. And then another simple one we can take a peek at. Let's do the SU2 and the SU1 because they managed to combine SU2 and SU1, sorry, SU2 and U1 together. That's what I'm going to look at next. It comes from the W and Z's working together. So D, this equation again. Oh, got to put this thing here, this thing here, and here. Let's see, 1 and 2. C1 and 2. We have this. Oh, this gets a little bit more complicated over here. We need two of these things. One on the left. I'm going to divide G by 2. This G is the SU2 coupling. That's the V there. This is now W mu. Nice W there. And this is how the W boson field works. And then here's tau. It's the A. And we have the same A. This is the index. Tracks this thing. So this is the little piece of that. And we have to keep going with it because there's more. We have to subtract IG. And this time we have this. But this time we use the U1 coupling. U1. There. This thing. It's just like this. But this now becomes uh, a B. This is the hypercharge. It's just gonna be the Z boson stuff. It's the Z boson. Alright. So this is how electroweak interactions occur. Still have to basically take all this stuff, put it in parentheses, and insert that. Alright, good enough on this one. Covariant derivative, the minimum dimensions necessary. This just allows us to take derivatives in any direction that we choose, these derivative combos, these interaction groups. And then these are the different coordinates that we're deciding to use, the different numbers. There's just and then the strong, the 3 by 3. This is how this works. It's the easier one. Just gonna grab this and move it down here. Because they weren't able to combine this yet. And here's the gluon SU3 group. Well, we have the quark field here instead. Quark field. And just put these keys everywhere. Q, Q, GS. This is the strong coupling constant. And then this G, mu, T. That is T. T. 15. And when he does the A's again. Wait, T? What's up with that? T, Okay, this is the gluon field. Gluon field. So the quark field interacts with the gluon field, and this, the T's. So we need some A up there, and A over here. And these are this thing here are the SU3 generators, which are the Gell-Mann matrices. Those are the 3 by 3s on this page over here. Well, imagine them as just being bigger versions of these. These are the generators. And I'm going to guess Actually, 1 second before I move on to that. I've never seen this interesting thing before. So we take T A, T B, and put them in a little pairing here. Set that equal to I, F, A, B, C, and then here's T to the C. My hand's starting to hurt. What did we just do right here? These are apparently structure constants. Well, we might as well look at what the gluon field tensor looks like. Oh, I wish I had less pain in my hand. So I could write this a little bit easier and quicker. What is this? Let me just write this out. V is equal to use this one. D mu GV minus dV G mu. Mu plus GS G mu parentheses brackets. Alright, this represents self-interactions. Let's see. Well, we can look at the Lagrangian and stuff. Let's not worry too much. Not go too far into this stuff. We're just seeing how, like, oh my god, okay, so now we have to learn about all this stuff if we want to understand how this works. I haven't just put this like right over here or something. Alright, I think we are almost done with this page. There's something really important about eigenstates. We have a wave function. T was if we have a alright, yeah, let's do stuff that I kinda get. Let's look at the Higgs field. So the Higgs field, we have this V, and then there's a potential. There's a voltage. There's going to be a self-coupling constant here. And then we could take this thing. And we can start to, we can take an absolute value, square it. And what happened there was we basically took the annihilation, sorry, the creation and annihilation and multiplied them. That's what the squaring thing is there. And then we have minus an expectancy value, or the VEV. What is that again? I want to get a good name because I don't know what the heck that means again. I was looking at this a few days ago. And then square this. Square that. Okay, and minimum energy gain. Essentially, what we're trying to do is we are trying to describe the symmetry breaking that's occurring in the Higgs field here. So this thing here, it's got two components to it, the top and the bottom. That and that. This is neutral, this is charged. So there's two components. I believe this is the Higgs potential, we can call this here. Higgs potential. So we have a neutral potential, or we can have a charge potential from the Higgs. Now, before breaking, essentially we're going to describe some symmetry during breaking. Symmetry, breaking. Symmetry, breaking. So what happens before breaking? Give you some space here. Before breaking, we have this 0, 0. Okay, this is fully symmetric, and therefore all particles massless. Just want to take a note that this SU2 is for left-handed, and this is the Y of hypercharge. Oh no, L is weak isospin. Here, check it out. These are the 2 by 2 Pauli matrices right here. This is more appropriate for the electroweak of the 2 by 2s. Yeah, here's just an example of derivative combos. So we're essentially saying, okay, let's take that one and that one and like multiply them by 1 that way. So we're rotating these things. The other ones have other things, and then we have to couple them. So we're rotating things around by 1s or i's or -1. It's interesting stuff. Mm, so these are rotations. This was the weak isospin. And collective charge. So what happens before symmetry breaking? We have zeros, the particles are massless. Then all of a sudden we break. And this thing gets a potential on one side. It's going to be this V thing right here, which will be denoted green. Divided by the square root of 2. I'll make this a little bit better looking. V over root 2. And there's a 0 on top. Good enough. Boom. Now, as we can see, that is not symmetric. Essentially, the Higgs, it just chooses a direction. And because of that, we have to do some Fourier transform from basically 0 to 1. We had to flip something positive, so we could say like 1 times this. At the same time, we had to get some kind of a wave function collapse. That's what happens when you choose a direction, right? Basically, what happens is that something tunneled through curved time. Tunnel through curved field. We'll call it an O field. We'll call it a time tunnel. Because time pushed it forward, and the O field was curved, and the wave function collapsed right in the middle and spawned this particle here. Kind of think like a water droplet forming and then getting big enough to finally drop. That's essentially what's going on here. So we have like see if we can try to draw this little picture. And we got the ceiling, it's empty. Here we notice that there's like, oh, there's like a water droplet forming here. Here's the ground. And then all of a sudden, it's like gonna fall through the air. Need some more room. Can I move the other stuff up a little? Sure, whatever. Up there. Then I can move this. And then we can look at how the water droplet forms. Or it'd be nicer if it was like copied well. Take that one, get rid of the drop, Here, we also this, and the drop is falling. What's interesting is that eventually this process will essentially reverse to the next 0 point, and that'll be nice. So this thing is kind of like now flipped. The vertical, and it's kind of like that. And there we go. Mm, looks like garbage. All right, so essentially what's going on here is that this is 0. This is now all of a sudden 1 popping up in thin air here. 1 times whatever you need. And then right here, back to essentially 0. And that is kind of how this seems to be working here. Right. I think that just about covers the standard model. Um, and the only other detail we can say is that, you would expect this to be exactly at half, or at exactly 1, or, whatever. The thing is, these particles, they don't always appear exactly right there. This is probabilistic. The probability that, I believe what we are measuring in the wave function, when we look at these things, notice this little piece of curvature here. This little piece of curvature is telling us that this location right here, right there, is high probability. And it may not be exactly right there, but the idea is that there's an optimal point of high probability. There's a high probability that it's going to spawn about over there when it does this rotation, but it doesn't always end up there. It tends to end up in other locations. And so that is essentially how we can consider that perhaps this quantum gravity model can help us to understand these quantum effects will move particles down the line. Uh, Maybe not yet, but there's several more pages here that I have to get through in order to fully establish this proof. But so far, it's adhering to the rules of the Standard Model, the idea that we want to start with zero Higgs, uh, these real zeros that are sort of going from here to here. The zero spins out, becomes a particle, spins back, becomes back to zero, spins out and becomes a particle, and spins back to zero. That is the mechanic that these zeros can work together to spit out particles. And sort of eventually they sort of want to slide down these zeros. You could think about just, this sliding it down. So, yeah. And yes, we did need 11 dimensions. All of these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 to be able to describe all the interactions between real and imaginary components of space and time. And then there's just these different combos which allow us to sort of pair these things depending on what direction we want to rotate them. And this can be a 1 by 1 or a 3 by 3, or potentially a 4 by 4 if we start looking at gravitons. So, very, very interesting indeed. This is how that potential forms. This is very important that the